Radioactive decay. Nuclear stability is a central topic of this lesson. Nuclear stability can be considered from both a kinetic and a thermodynamic point of view. Thermodynamic stability refers to the potential energy of a particular nucleus as compared with the sum of the potential energies of its components, protons and neutrons. While kinetic stability describes the probability that a nucleus will undergo decomposition to form a different nucleus, a process called radioactive decay. Of the approximately 2,000 known nuclides, only 279 are stable with respect to radioactive decay. Tin, with 10 nuclides, has the largest number of stable isotopes among those 2,000 known nuclides. It is instructive to examine how the numbers of neutrons and protons in a nucleus are related to its stability with respect to radioactive decay. The figure at the right side shows a plot of the position of the stable nuclei as a function of the number of protons, say, and the number of neutrons, A minus A. The stable nuclides are said to reside at a zone of stability. Those at the red dots are the nuclides resides at a zone of stability. We have here lithium with atomic number of 3 and mass number of 6. And at the upper portion, we have mercury with 202 atomic mass and 80 atomic number. Here are the following important observations that are concerning with this radioactive decay. All nuclides with 84 or more protons are unstable with respect to radioactive decay. Like nuclide are stable when say equals A minus A, or protons is equal to protons, which make a ratio of 1. However, for heavier elements, the neutron-proton ratio required for stability is greater than 1 and increase with number of protons. Certain combinations of protons and neutrons seem to confer special stability. For example, nuclides with even number of protons and neutrons are more often stable than those with odd numbers, as we will show at the next slide. There are also certain specific number of protons or neutrons that produce especially stable nuclides. These magic numbers are 2, 8, 20, 28, 50, 82, and 126. This behavior parallels that for atoms in which certain numbers of electrons. This table shows the number of stable nuclides related to number of protons and neutrons. As we can see, for an even number of protons and even number of neutrons, there are a lot number of stable nuclides. Compared with odd number of protons and neutrons, there are only 4 stable nuclides, meaning there are more unstable nuclides with an odd number of protons and neutrons. Radioactive decay. Radioactive nuclei can undergo decomposition in various ways. This decay process fall into two categories: those that involves a change in the mass number of the decaying nucleus, and those that do not change its mass number. Radioactive decay, also known as nuclear decay, radioactivity, radioactive disintegration, or nuclear disintegration, is a process by which an unstable atomic nucleus loses energy by radiation. A material containing unstable nuclide is considered radioactive. Three of the most common types of decay are alpha decay, beta decay, and gamma decay, all of which involves emitting one or more particles or photons. This weak force is the mechanism that is responsible for beta decay. There are six fundamentally different kinds of nuclear decay reactions, and each releases a different kind of particles or energy. The essential features of each reaction will be discussed in the succeeding slide. The most common are alpha and beta decay and gamma emission, but the others are essentially to an understanding of nuclear decay reactions. So let's jump to the first type of radioactive decay, which is the alpha decay. Many nuclei with a mass number of greater than 200 undergo alpha decay, which results in the emission of a helium-4 nucleus as an alpha particle. The general reaction is as follows. So this alpha particle is actually an helium with 4 atomic mass. The daughter nuclide, or the product of the decay, has 2 fewer protons and 2 fewer neutrons than the parent. Thus, alpha particle emission produces a daughter nuclides with a mass number A-4 and a nuclear charge of say-2 compared to the parent's nuclide. An example is radium-226 undergo alpha decay to form radon-222. Because of nucleus are conserved in this and all other nuclear reactions, the sum of the mass number of the protons, 292 plus 4, is equal to 226, which is the atomic mass of the parent nuclide, which is radium. Similarly, the sum of the atomic number of the products, 86 plus 2, is equal 88, which is equal to atomic number of the parent. Thus, the nuclear equation is balanced. Just as the total number of atoms is conserved in a chemical reaction, the total number of nucleons is conserved in a nuclear reaction. Beta decay. Nuclei that contain too many neutrons often undergo beta decay, in which a neutron is converted to a proton and a high-energy electron that is ejected from the nucleus as a beta particle. So again, an unstable neutron in the nucleus is being transformed into a protons which remain on the nucleus, and a beta particle, which is an electron being emitted by the nucleus. The general reaction for beta decay is therefore this one. Although beta decay does not change the mass number of the nucleus, it does result in an increase of one atomic number because the addition of a proton in a daughter nucleus. Thus, beta decay decreases the neutron to proton ratio, moving the nucleus toward the band of the stable nuclei. So again, since one neutron is being converted into protons, therefore our atomic number will be added by 1 as represented as a presentation to the proton or due to the neutron that being changed into a proton. So for example, a carbon-14 undergo beta decay to form nitrogen-14. So once again, the number of nucleus is conserved and the charge are balanced. The parents and the daughter nuclei have the same mass number since the electron has 0 atomic mass number. And the sum of the atomic number of the product is 6, which is the same as the atomic number of the carbon-14 parent. Positron emission. Because a positron has the same mass of an electron but opposite charge. Again, positron means a positively charged electron. Positron emission is the opposite of beta decay. Thus, positron emission is characteristic of neutron-poor nuclei, in which decay by transforming a proton to a neutron and emitting a high-energy positron. So this is the opposite of the beta decay, in which the proton is being transformed into a neutron and emitted a positively charged electron. The general reaction is this one at the table. So like beta decay, positron emission does not change the atomic mass number. Again, positron emission does not change the mass number of the nucleus. So in this case, however, the atomic number of the daughter nucleus is lower by 1 than that of the parent. Thus, the neutron to proton ratio has increased, again, moving the nucleus closer to the band of stable nuclei. So, for example, carbon-11 undergoes positron emission to form boron-11. So, nucleons are conserved and the charges balance. The mass number 11 does not change, and the sum of the atomic numbers of the product is 6, the same as the atomic number of the parent carbon-11 nuclide. Electron capture. A neutron-poor nucleus can decay by either positron emission or electron capture, so in which an electron in an inner shell reacts with the proton to produce neutron. So in this case, that one electron in the inner shell is being reacted into a proton in which it produces a neutral charge, which is equivalent to a neutron. So when a second electron moves from an outer shell to take the place of the lower energy electron that was absorbed by the nucleus, an X-ray is emitted. Therefore, the overall reaction for electron capture is this. So electron capture does not change the mass number of the nucleus because both the proton that is lost and the neutron that is formed have a mass number of 1. As with positron emission, however, the atomic number of the daughter nucleus is lower by 1 than that of the parent. Once again, the neutron-to-proton ratio has increased, moving the nucleus toward the band of stable nuclei. So for example, iron-55 decays by electron capture. So EC stands for electron capture to form manganese-55, in which is often written as this one. So the atomic number of the parent and the daughter nuclei differ, although the mass number are the same. So the balanced nuclear equation for this reaction is this one. Must be explicitly include the captured electron in the equation. So we can see clearly the balance equation. So both positron emission and electron capture are usually observed for nuclides with low neutron-to-proton ratios. But the decay rates for the two processes can be very different. Gamma emission. Many nuclear decay reactions produce daughter nuclei that are in a nuclear excited state, in which is similar to an atom in which an electron has been excited to a higher energy orbital to give an electronic excited state. Just as an electron in an electronic excited state emits energy in the form of a photon. When it returns to the ground state, a nucleus in an excited state releases energy in the form of a photon when it returns to the ground state. By the way, photon means a particle, a light particle. So in this reaction, when it occurs, it produces light, which is the photon. And this photon is what we call the gamma emission. So these high energy photons are gamma rays. Gamma emission can occur virtually instantaneously, as it does in the alpha decay of uranium-238 to thorium-234, where the this asterisk denotes an excited state. So this thorium being excited when it being relaxed, then a gamma emission occurs. So if we disregard the decay event that created the excited nucleus, then this thorium being just emitted a gamma ray. So gamma emission can also occur after a significant delay. For example, a technetium-99m has a half-life of about 6 hours before emitting a gamma ray to form technetium-99. Because gamma rays are energy, their emission does not affect either the mass number or the atomic number of the daughter nuclei. That's why in this example, thorium, the atomic mass, the mass number and the atomic number is not being changed. Gamma ray emission is therefore the only kind of radiation that does not necessarily involve the conversion of one element to another, although it is almost always observed in conjunction with some other nuclear decay reaction. So last type of radioactive decay is spontaneous fission. Only very massive nuclei with high neutron to proton ratios can undergo spontaneous fission, in which the nucleus breaks into two pieces that make different atomic numbers and atomic masses. This process is most important for the transactinide elements with atomic number of greater or equal to 104. Spontaneous fission is invariably accompanied by the release of large amount of energy, and it is usually accompanied by the emission of several neutrons as well. An example is a spontaneous fission of californium-254, in which gives a distribution of fission products. One possible set of products is shown in this equation. So once again, the number of nucleons is conserved. Thus, the sum of the mass number of products 118 plus 132 plus 4 is equal to 154, which is equal to the mass number of the reactant. Similarly, the sum of the atomic numbers of the products 46 plus 52 plus 4 atoms times 0 is equal to 98. Is the same as the atomic number of the parent nuclei. Sorry, that's not neutron. That's not for atom. Rather, it's for neutron. So in this case, Californium is being transformed into palladium and technetium and technetium, thorium. Sorry, I forgot T. And 4 neutrons. Okay, so let's check your understanding in this lesson. So do this one and write your answer in the comment section.